So thank you very much for inviting me to give both talks, and thank you for allowing me to do it in one talk. And thank you everybody for coming to listen to me. When I was a graduate student, one of the first things my supervisor, whom we all know, taught me was the last speaker thanks the organizers before their talk. So I would really like to thank the organizers for organizing this wonderful meeting. It's, as many of you know, I only caught half of it, but the half that I caught, I've really been enjoying myself. It's very hard to find time to work because the talks are so good. So really, thank you for all the work you've put into it, and hopefully there'll be more. My supervisor didn't tell me to clap, sorry. All right, so this talk was about coloring graphs with forbidden, well, it says here paths, but actually it's going to branch out of that a little bit. And really this is a summary of much of my work over the last 4 or 5 years. So few things here will be very new, but it will kind of give an overview of a topic that I've become interested in the last few years. And different results are joined with different people, so I'll say what's joined with whom. All right, so coloring is hard. If I give you a graph, it's hard to color it. It's even hard to 3-color it. And it turns out it's even hard to approximate a 3-coloring. If I give you a graph and I want you to come as close as possible to 3-coloring it, the best people can do is what it says there. Maybe it's been improved a little bit recently, but you can't do like log n, or certainly you cannot do a constant. It's incomplete to do a constant, so really very hard problem, 3-coloring. So then you ask yourself, well, what if the input is not completely general? What if I promise you that something is missing from the input? There are many ways in which you can restrict the input, but I work on induced subgraphs, so I'm interested in what happens if what I know about the input graph is that certain induced subgraphs are missing from it. And it turns out for most things that you might consider excluding, it doesn't help at all. So first of all, there is a theorem of Kaminsky and Lozhin that 3-coloring, or in general k-coloring for any k at least 3 graphs of high girth is still NP-complete. And that means that if what I exclude has a cycle, that's not going to make the problem easier, right? Because I excluded a 100-vertex graph and it has a cycle, so all graphs with girth at least 101 don't contain this little graph that I excluded, and it's hard to color them by this theorem. So if you hope to have some success by excluding something, you should be excluding forests. But it gets even worse, because edge coloring is NP-complete. So that means vertex coloring line graphs is NP-complete. And that means if I exclude anything that contains a claw, right? I'm excluding a graph H and H contains a claw, then the class of line graph is H-free, and it's hard to color them. So if you're going to exclude something, not only does it need to be a forest, it needs to be a forest that doesn't contain any claws. And if you think about that for a second, what that means is that every component of your forest is a path. But this is an important class of graphs that has a name. It's called linear forest, I'm told. And for the first half of my talk or so, I'm going to focus on the case when what we're excluding is just one path, right? So I'm allowed to exclude this joint union of paths. What if I exclude just one path? What can you say? And just to set up convention, I'm going to write P sub t to mean a path with t vertices, not a path with t edges, a path with t vertices. And of course, this is only important if you're actually going to think about these problems. Otherwise, sort of the impressionistic description of excluding PT is the same, whether it's vertices or edges. Okay. So there's a table that represents our current state of knowledge, and I'm going to explain to you what it means. So first of all, we're excluding paths, and you can exclude paths of different lengths. And you can also try to color with different number of colors. And yeah, it's for every path length and number of colors, you can ask what's the complexity of K coloring a PT free graph. And if you're trying to two-color, that's always easy. So we only start with K equals 3. And then, so then this table represents what we know. And then the colors roughly mean who proved what. So I'm going to try and explain it now. So first of all, if you exclude a path on at most 5 vertices, then everything is polynomial. And these are, so I'm not going to, so first of all, almost everything I know about this problem comes from this survey. And that's, so that's what I wrote as a reference, but it's a survey paper, so different people prove these theorems. So if you exclude a path of length 5, or path of length at most 5, then no matter how many colors you want to color with, it's polynomial. And it makes sense, right? If you exclude a path on 3 vertices, your graph is just a union of cliques. If you exclude a path on 4 vertices, your graph is either not connected or not connected in the complement. If you exclude a path with 5 vertices, it's harder, but you can still do it. So then when you exclude a path with 6 vertices, it gets a little more interesting. So it's polynomial if you're trying to 3-color. It's NP-complete if you're trying to 5-color or more. And it's open if K equals 4. It's very odd. There's this little open sporadic case. With a group of people, we are working very hard on this problem now, but I still don't know if it's polynomial or NP-complete. I tend to believe now that it's polynomial, but I still don't know. So then for T equals 7, we know that 3-coloring is polynomial, and this is a relatively recent result with this group, and I'm actually going to tell you something about the proof, because everything I know how to prove in this area roughly follows the idea of this proof, so I thought I'll show you this proof. And then it's NP-complete from K equals 4 and on, right? So if you're trying to color with at least 4 colors and the graph is P7 free, then it's NP-complete. And so when K is at least 6, that was already known at the time of the survey. When K is 4 and 5, that's a new result of Huang. And then if you're excluding a path of length at least 8, then it's NP-complete for at least 4 colors. That's been known for a while. But it's open for 3-coloring. So, I mean, the problem I most like in this area is what happens to 3-coloring if you exclude P100 or P1 million? I mean, is 3-coloring actually sufficiently easy that even if you exclude a very long path, it's still polynomial? And somehow, so 3-coloring is really different from 4-coloring, just like 2-coloring is really different from 3-coloring? Or is it the case that just, if you exclude P million, nothing good happens? 3-coloring is hard. So, I mean, that's the question I would really like to know the answer to, but I don't know how to do it. So the first thing I want to do is talk a little bit about this proof, as I said. And many of the tools are useful for other things also. All right, so I guess I forgot that I had this slide. So let's review the open cases. We have K coloring, so 3-coloring PT free graphs when T is at least 8, and then 4-coloring P6 free graphs. And on this, so let me just say a couple of words about this, because it's a problem I'm currently interested in. I'm working on it. So first of all, this is pretty close to being NP-complete. The least version is NP-complete, right? If I'm not 3-coloring, but I have least for every, right? So you know what least coloring is. You want to color except every vertex has an allowed list of colors. And least 3-coloring means the least a subset of, or least 4-coloring means least a subset of 1, 2, 3, 4. And that problem is NP-complete. So no P6, you can even exclude C5. And sorry, yeah, so I didn't write it here, but P6, C5 free graphs, it's NP-complete to do the least coloring version. But the normal 4-coloring version is polynomial. That's a theorem with Peter Marcelli, Uri Stacho, and Mingshan Zhong. So there's really a difference, right? I mean, the kind of moral difference is if you're doing 4-coloring and you see, oh, here's the vertex and I cannot color it color 3, you can trace it back and figure out why you can't color it color 3. If you're doing a 3 coloring, and the way you trace it back, you build some path to the thing that, that tells you can't color this vertex color 3. But on the other hand, if you're doing the least coloring problem, then here's the vertex and you're not allowed to color it 3 just because 3 is not in its list, and that doesn't allow you to build any interesting path. So this is sort of a very high-level description of this. So this is polynomial if you exclude P6 and C3, and that's the theorem of these people, except there's no B at the end of Tevis's name. I'm sorry about that. And recently with Paul and Sophie Sperkel and Ming-Shan Zhong, we were thinking about the structure of these graphs. Right? So they have an algorithm, and actually they came pretty close to having a structure, but not quite. And we were trying to really describe what all these graphs look like, and we have such a description. It's fairly nice. There are like 4 classes of basic graphs, and then there's one operation you do, and it's safe for keeping the graph P6 and C3 free, and it's a 25-page paper, which in forbidden induced subgraphs is nice and compact. So anyway, so that's what I wanted to say about this problem. But now let me move on to 3-coloring P7 free graphs. And again, that's a theorem with Flavia Bonomo, Peter Macelli, Oliver Schaud, Maya Stein, and Ming-Shan Zhong. So there are two main tools to this. The first tool is that we want to think about list coloring. And I already said what list coloring means. For every vertex, you have a list, and you want to color so that each vertex is colored from its list. And then the idea is to start with your original problem and reduce it to a bunch of list coloring problems, polynomially many list coloring problems. And then in such a way that your original graph is colorable if and only if one of those list coloring problems has a solution. And then what you want to achieve is that the least coloring problems you can solve. Right? And of course, the way to think about it, you pre-color something, and now that tells you that some other vertices, certain colors are not allowed for them anymore, and now you just focus on the part that wasn't pre-colored but lost some colors because you pre-colored something. And then you branch on what you pre-color, and you got your polynomial many list coloring problems. And I'll do more details of this in a minute. So now the second tool is what allows you to solve some of this list coloring problems, or all of these list coloring problems efficiently. And that's the Theorem of Edwards that says that if I give you a graph, and you don't need it to be P7 free, you don't need to know anything, and so you have a graph and you have lists, and the lists have size 2. So every vertex has only 2 allowable colors, then you can solve this problem in polynomial time. You can determine whether the graph is colorable from this list. Sorry, I should stop doing that. You can determine whether the graph is colorable from this list in polynomial time. And if you know how to record the coloring as an instance of K-sat, then you see immediately why this works, right? So how do you make a K-sat problem out of coloring? For every vertex, you have variables that say this vertex colored 1, this vertex colored 2, this vertex colored 3, and so on. And then for every edge, you have a clause of size 2 that says either this is not colored die or this is not colored die. And then and these are nice clauses of size 2. And then for every vertex, you have a clause that says it's colored 1 or it's colored 2 or it's colored 3 or it's colored 4 or it's colored k. But this is the only bad clauses. This is the only thing that separates general coloring from being two-set. So if I promise you that every vertex has only 2 available colors, then the big problem is gone. So that's this theorem. And secretly what we do in this reduction is we reduce our 3-coloring problem to polynomially many problems, in each of which all lists have size at most 2. Okay, so that's the first tool. And then the second tool is a theorem of Campi and Schaud that, right, so I said we're going to pre-color something, but you need to pre-color carefully if you're hoping to pre-color something and reduce all this to size 2. So that's the theorem that starts us off on that. So they have a theorem that says that if you have a PT-free graph, then in it there is a connected dominating subgraph. So you know what connected means? Dominating means everybody outside of it has a neighbor in it. And this subgraph, either it's just PT minus 2, or it's PT minus 2 free. So somehow, right, you have a PT free graph, there's in general PT minus 2 free graph in there that, that in some sense is a big chunk of your graph, and that sense is that everybody else has a neighbor in it. All right, so let's see how this works. So there are two cases here. Maybe the dominating graph is PT minus 2, or maybe it's PT minus 2 free. Let's do this case first, because it's much nicer. So if you're in this situation, then actually you have a dominating subgraph which is bounded size. It's size t minus 2, right? So then what you do is, here's your PT minus 2, and here's everybody else in the world, and everybody else in the world has neighbors here. So then you try all possible pre-colorings of this, right? This is bounded size graph, so you can try every pre-coloring of it, and then everybody here lost at least one color from its list. And then you just solve a problem with all lists having size at most 2 on this graph. And so that's your polynomially many list coloring problems where all lists have size at most 2. So that's a nice case. That's kind of shows you the idea. So now let's do the less nice case. And this, I didn't use P7, I didn't use anything, but now I'm going to use P7 fairly heavily. So I'm thinking about a P7 free graph. That means it has a dominating P5 free subgraph. Well, P5 free graphs are complicated. I can't just do this trick on a P5 free graph. But again, by their theorem, a P5 free graph has a dominating subgraph, which is either P3, right, which is just a 3-vertex graph, or it's P3 free, which is an easy graph, right? Graphs with no induced 3-vertex paths are just unions of cliques, and this graph is connected, so it's just a clique. And all I want is to 3 colors, so it's a clique of size at most 3, because if there's a K4, I can stop right away. So I'm not in this situation, but I'm in a situation where I have a bounded size subgraph, which is either a clique or a P3, so that everybody in the world is distance at most 2 from it, right? This was dominating, and then this is dominating in here. So that's not as nice as we had it before, but it's something. So now basically you start working on this graph, trying to make it to look more like this. So the first thing you do, there is a tool here that I don't know if it's hard or easy. It seemed very complicated to me when I first saw it, and now I think it's easy, and I don't want to kind of spend too much time on it, but I'm going to say it a little bit slowly. So we would like to examine all possible colorings, right? But we can't. There are too many colorings. We can only examine polynomially many things. So instead of looking at all colorings, you find a bunch of important vertices. And then you don't look at all. So let's say every coloring is somehow defined by 10 important vertices. So I can't look at all colorings, but I can look at all 10 tuples of vertices and think about all colorings where these 10 vertices are important. And that's sort of how the branching goes. You understand what vertices are important, and you guess them all. And now for every guess, you can think about all the colorings that come from this guess. So I'll keep talking about guessing vertices and guessing their colors, and that's what I mean. There are some important vertices, and I can classify all colorings by just looking at these important vertices. So we're going to guess about 20 vertices, and we're going to arrange that I have the same pictures here, where I have a pre-colored. So here this was bounded and pre-colored, and then there were people at distance 1 and people at distance 2 from it. Now I'm going to arrange a similar kind of picture where this part is pre-colored, and then here everybody has a neighbor there, and here everybody has a neighbor there, and in addition, I want to say that y prime is stable. And I now realize I'm lying to you a little bit. Here it says the new S prime is only S plus 20 vertices. That's not actually true. The new S prime is, I guessed 20 vertices, but then, if I pre-color these 20 vertices, there might be a much bigger portion of the graph that became pre-colored. And for various reasons, I want to push all of it into this S. So that's kind of technical, but what it says there at the moment is false, so I don't want to not say anything about it. So let me just give you a rough idea of how you do it. So here it is at the very start. You have your S, which is at the moment very small. You have your set X, where everybody has at most 2 colors in their lists. And then you have your set Y, where everybody has 3 colors. And then, so let's look at different lists in X, right? It was a 3 coloring when I started, so the possible lists are 1, 2, 1, 3, and 2, 3. And then Y at the moment, there's, it's complete wilderness. I don't know what's going on. So, and I would like to turn Y into a stable set. Now, a good way to turn something into a stable set is to prove that the components are homogeneous sets. Homogeneous set means no vertex is mixed on it. No vertex has both a neighbor and a non-neighbor in it. So suppose there's some component of Y that's not a homogeneous set. So then there's some vertex in X that's mixed on an edge of Y. And now so now I'm going to guess this vertex and guess those 2. And suppose I manage to guess all of this in such a way that, this is colored 1 or 2, and this is colored 1 or 2, and this is, of course, colored 1 or 2. Now I claim nobody else in this set can give me the same trouble as he does. Because let's look at some other vertex here. Is it possible that it also is mixed on an edge? And it's on an edge of Y, so it's on an edge where, these guys still have 3 colors available to them. So then what does it mean? He cannot be adjacent to any of those, because if he were, he would lose a color. So he would not be in the set with lists 1, 2. They cannot be adjacent to any of those, because, again, if they were adjacent to any of them, they would lose the colors. They wouldn't be in the bad set of people with lists of size 3. So there are no edges between this and that, but both of those have neighbors in S, and S is connected, so I can connect them up by a path. And now this is too long. This is at least length 7. And, and then there are other cases. So now what do I know? Now I know there's no coloring where some vertex with list 1, 2 is mixed on an edge of Y, and this colors are in 1, 2, and this colors are in 1, 2. So then there are 20 more cases, but that's how it starts, and they're all kind of like that, but harder. Okay, so you managed to make Y stable. Now there's another trick of similar kind. So let's do that trick. Here I have my S, and again I'm going to draw X already partitioned by its lists. So note that S is now, it's unbounded size, but I've colored everybody in it. I've colored every vertex in it, and by branching not too many times. So now let's look at the vertex here. So first of all, I want to know, can there be a coloring and a vertex in Y so that it has a neighbor colored 1 here and a neighbor colored 1 there? So if there is, guess it. Here, 1, 1, and let's say he's colored 2 without loss of generality, so I guessed all of this. Now, can there be another vertex that also has a neighbor colored 1 here and a neighbor colored 1 there? So let's look at some other vertex that potentially has this property. It has a neighbor here and a neighbor there. Now, it's meant to be in this green set. Now, I claim there are no edges among these 4 vertices, right? If this black were adjacent to this or that, I would know he's not a 1. And I want to know, can he have a neighbor colored 1? If these 2 were adjacent, I would also know that not both of them are 1s. So among these 4, there are no edges. He is not adjacent to anything in the green path because he has 3 colors. If he were adjacent to anything in the green path, he would lose a color. The only possible edge that I might have is this edge, because this is colored 3, his potential this is color 2, his potential colors are 1 and 3, so even if this edge is present, that doesn't tell me anything about this guy's colors. So, so let's first do the case when this edge is not present. Then what you say is, so this S is connected, and you need to be a little bit more careful, and you need to arrange that either there's a path like this where those two don't have neighbors, or there's a path like that where those two don't have neighbors. And let's say it's like this, doesn't matter very much. And then if you can arrange that, then you go 1, 2, 3, 4, 5, 6, 7. That's a 7-vertex path. And then the other case is, and if the path is in the other place, it's exactly the same. If this edge is present, then you do something a little bit more careful. Let's see, sometimes I can do it. 1, 2, 3, 4. So that's already good. You know what, let me not. There's a 7 path you can find there, but you need another axiom about that I haven't told you about, so it wouldn't be very enlightening for you anyway, so let me skip that. So anyway, so what just happened? Oh yeah, I'm sorry, I got too excited about paths. So what did we prove? We proved that nobody in the world, so by guessing a few vertices, we can arrange that nobody in Y has a repeated color. Has both a 1 here and a 1 there, and similarly, these are 1, 2s, these are 1, 3s. Similarly, you can't have a 3 here and a 3 there, and so on. So now let's think about somebody in Y. If he has a neighbor in each of these 3 sets, then contradiction, the graph is not colorable, because he's not allowed to have any repeats, so there isn't a color for him. If he only has neighbors in 1 set, then I can just delete him, because he has 3 colors available for it, and all its neighbors are colored 1, 2, have lists 1, 2. So there are many cases when somebody in Y has neighbors in exactly 2 sets. And let's say it's like this. So then what? Is it possible that both 1 and 2 appear here? Could there be a coloring where both 1 and 2 appear here? Well, the answer is no, because if both 1 and 2 appear here, 1 is not allowed there because there are no repeats, so all of this would be 3. And again, there's no color left for him. So if there is a coloring, then this is monochromatic and that is monochromatic. And on the other hand, if you manage to arrange that this is monochromatic and that is monochromatic, you can always color him. So then what you do is you delete him and you contract those 2 singletons and keep going. So what happened? What happened is that we got rid of all of Y. Either we were able to move vertices of Y into X and reduce their lists, or we were able to say, actually, this vertex doesn't matter. If I manage to color everything else, then I can extend the coloring to this vertex. And then that's exactly what we wanted, right? Yeah, so that's this. We guessed some more colors, and then now all the lists have size at most 2, and we can apply Edwards' theorem. So that's how this proof works. And now let me switch gears a little bit and talk about some other related theorems. So there's somehow 2 related questions. One is there a polynomial time algorithm to let's say 3 color? And then the second question is it true that all abstractions have bounded size? All minimal abstractions have bounded size? And if all minimal abstractions have bounded size, then that's a very easy algorithm to color, to test if there's a coloring. And so Paul Simmer asked this question. Are there boundedly many abstractions for 3 coloring PT-free? So are there boundedly many PT-free abstractions, minimal PT-free abstractions to 3 coloring? And the answer is not in general. So Alexei Pokrovsky constructed an example of an infinite family of graphs with no 7-vertex paths, all of which are minimal abstractions to 3 coloring. But on the other hand, for T at most 6, it is true. And that's a theorem with Goet, Geber, Schout, and Zhong. And I should say Ming-Shan talks was basically the details of this theorem. And so I'm going to say something about this theorem, and there's going to be some overlap, but I'm going to do significantly fewer details that Ming-Shan did. So, okay. So this is sort of interesting. We have a polynomial time for coloring those, for 3 coloring those, but there are infinitely many abstractions. So I don't know what that means, but it's something. And then Goldwach, Johnson, and Paluzma and Song asked a more general question: for which H are there finitely many H-free for critical graphs? So H-free means minimal non-3 colorable, right? For critical means minimal non-3 colorable. And so this is a problem I'll talk about from now on. So first of all, I should say we answered this question, we solved the problem. That's the next thing I'll talk about. Let me just have a word, because this is kind of hard to say and keep in your head all the time. I'll say H is powerful if, when I exclude H, there are only boundedly many abstractions for 3 coloring, right? So powerful means the answer to this question is yes. So what this slide says is that P7 is not powerful, but P6 is powerful. Okay. So let's see what could possibly be true. So which graphs are not powerful? First of all, if I know that 3 coloring is still NP-complete when I exclude something, then this something is not powerful, right? And it can't be that there are only boundedly many minimal non-3 colorable graphs. So the claw, I know excluding claw keeps the 3 coloring problem NP-complete, so the claw is not powerful. I know that excluding a cycle keeps the problem NP-complete. Or excluding anything with a cycle. So graphs that contain cycles are not powerful. So again, the only things that have a chance of being powerful are linear forests. So in this sense, we're exactly in the same place as we were with just asking when there's 3 coloring polynomial. But like I said, there's a difference. So I mentioned Pokrovsky constructed an infinite family of P7 free graphs that are all minimal non-3 colorable. And actually, if you look at his construction a little bit more closely, his graphs don't even have this induced subgraph. So this graph is not powerful. Right? You exclude this, it doesn't give you boundedly many minimal abstractions. Okay, so now I can tell you the answer. So a graph is powerful if and only if it's a subgraph of one of those. And so what are these? P6, right, a 6-vertex path. Then there's this graph, this joint union of 2 3-vertex paths. And then there's this graph, which is right, a 4-vertex path and a stable set. And this, I don't care what size it is, the stable set. All right, so basically, most graphs are not powerful. Even graphs where you have a chance that 3 coloring becomes polynomial, still most of them are not powerful. And then there's a related problem, right? There's coloring and then there's least coloring. So what if I give you a graph and every vertex has a list, and the list is a subset of 1, 2, 3? And I want to know, so there are various things I want to know. I might ask when can you color this in polynomial time, or I might ask when there are boundedly many abstractions to that problem, or to that kind of problem. And so I'm going to say graph is least powerful if excluding this graph gives me boundedly many abstractions to this problem, to the least coloring problem. And you can ask which graphs are least powerful. And it turns out it's different. It turns out the graphs excluding which gives you boundedly many abstractions to 3 coloring are different from the graphs excluding which gives you boundedly many abstractions to the least version of the problem. And the reason is that this graph, it's powerful, but it's not least powerful. And I'll explain some of the reason in a little bit. All right, so the next thing I want to do is tell you a little bit about the proof. And the proofs are very similar, basically. So I'm going to focus on, I want to find the theorem I'm going to prove. Here, I'm going to mostly talk about the proof of this, but the proofs are very similar, and in the one place where they differ, I'll tell you where they differ. Or in the one place where they differ significantly, I'll tell you where they differ. All right, so first of all, if a graph is not powerful, then all its supergraphs are not powerful. If a graph is is powerful, then all its subgraphs are powerful. And armed with this knowledge, you can think about it for a minute and figure out that it's enough to prove that these graphs are powerful. Okay, and the way we do it is basically we try to follow this outline. We try to pre-color something and then and then see if we can reduce the problem to a problem where all these have size 2, and then there's another branch of the proof that says if a graph is in one of these families, right? So it's free of one of those, and all these have size at most 2, then the minimal abstraction, all minimal abstractions have bounded size, right? So here, as soon as we had all these size at most 2, we stopped because there's Edwards' theorem. There, we need to prove another lemma that says, actually, when all these have size at most 2, the abstractions have bounded size, but basically you can. The issue, so that's a smaller issue. I mean, it's a theorem you need to prove, but you can prove it. The bigger issue is that you need to be more careful with what you're guessing. Let me see if I can say it more clearly. Okay, so maybe let me not say it more clearly. I can't think of a nice example at the moment. But right, when we're doing the 3-coloring problem, basically, as long as it was a bounded number of words, I could guess anything I wanted about them. When you're trying to do this, you need to be more careful. You can't branch quite so much. So we are trying to use the same method, except we're a little more limited. But let me tell you how the method works after all. So, like I said, the first step is we want to prove that if here is a graph and it's H-free where H is one of those graphs, right? One of those graphs that I'm working on, then sorry. Just make sure what I wrote here. Yeah. Then it contains a subgraph G prime, so that everybody here has least of size at most 2. And the whole graph is not much bigger than this, right? V of G is, so I wrote at most 10 to the 6 times that. But actually, it's much bigger than 10 to the 6, so some huge constant. And then the next step would be to prove that this is not too big, right? So. All right, so the next step is to prove that, that if I have a graph which is H-free and all these have size at most 2, and it's a minimal abstraction to 3 color, and it's a minimal graph that cannot be colored, then it's not too big. And this almost works. So this works for when what I exclude is a P6, and this works when what I exclude is a P4 plus a stable set. It doesn't work for this graph. There is a family of graphs that don't contain this as an induced subgraph, and it's an infinite family, and each graph is equipped with leasts all of size at most 2, and where every vertex has a least of size at most 2, and you can't color them, and every subgraph you can color. But that's where the difference between least coloring and real coloring comes in. So how do I get this graph, really? I pre-color something else, and then, roughly, everybody here has neighbors there, and then that's how they lost their colors. That's how their leasts went down to size at most 2. Well, so what's the difference? So what is the additional information I have? I know that in this graph, if somebody has least 1, 2, it's because he has a neighbor pre-colored 3. So even though I have that construction, I have the construction where I don't have this, and least have size 2, and it's not, it's minimal non-3 colorable. What I have in it, in fact, is a path that looks like this. So it's 1, 2, 3, 4, 5. And let's say he has list 1, 2. And then everybody else has 3 in their list. So it's something 3. And now what happens is, well, why is he 1, 2? It's because he had a neighbor that was pre-colored 3. And this guy, sorry, I'm thinking about the wrong problem. So it looks like that. And this guy is not adjacent to any of those, right? Because he is pre-colored 3, but they all have 3 in their list. And then in the graph I started with, there was my forbidden subgraph. Okay, so this is maybe a little too much detail, but anyway, that shows you the difference between list coloring and just starting with a general coloring problem and then pre-coloring a bit. So the next thing I want to do is explain something about how these 2 steps are done. Right, so this explains how you build something in your graph which is not much smaller than your graph and has all lists of size 2. And then the next step will be to roughly explain why abstractions with lists of size 2 are not very big. Okay, so here we go, more details. So I want to follow this outline and start with something pre-colored and try all colorings of it. Now, I'm only allowed to try all colorings of something if there aren't very many of them, right? You know, if there are boundedly many of them. If the subgraph I'm planning to pre-color has bounded number of vertices, well, that's great. It only has boundedly many colorings, of course. But you don't have to be so restrictive. There are graphs which are huge, and still they only have 103 colorings, and all of those you're allowed to try to pre-color. So that's the first observation we make, that it's not important to pre-color bounded size graphs. It's important to pre-color graphs with boundedly many colorings. So then what you do is, let's see. So you prove that there is a graph R, subgraph R that you can find, and it has only 1,000 3 colorings. And you try each of them. And then, okay, so now all of these guys, right, have colors. Now you can, if somebody has a neighbor here, then you can reduce his list. And maybe some guy outside had a neighbor colored 1 and a neighbor colored 2, so then his list got reduced to 3. Then if you go on further, you can reduce his list. And what I'm allowing to do is 3 steps like that. Right, so I said pre-color, update 3 times. That's what I mean by update 3 times. First, I look at neighbors of this R, and I reduce their list according to their neighbors in R. Then if there's somebody else who now suddenly sees the vertex with only 1 color in its list, I can update its list, and then I can do it 1 more time. And then the theorem is that after I've done that, after I've done this 3 steps of updating, all the lists went down to 2. Right? That's not clear at all, right? That's the structural graph theory proof that makes this work. But that is what I need. Now, why does this work? Why can I do it? So, I mean, sometimes it works nicely. For example, right, remember what we're excluding. There are 3 theorems we're actually proving at once. We're proving the theorem when H is P6, we're proving the theorem when H is P4 plus KP1, and we're proving the theorem when H is 2P3. So this is the nice one, because here, if I have P4 plus K minus 1 P1, right, then there are people with neighbors in it, but then there's nobody else, because I'm excluding a 4 path and a stable set of size K. So that works very nicely, right? This is sort of the easy case of everything. This graph has bounded size, so it has bounded many pre-colorings, and everybody in the world has a neighbor in it, so 1 step of updating is sufficient. When H is P6, then remember the theorem we just said, it has P4 free dominating connected subgraph. I mean, or a P4, or a dominating P4, but that's even better. So if it's dominating P4, then you win the same way you win here. If it's a dominating P4 free subgraph, you notice that it has to look like this. You can partition it into two parts, and the two parts are complete to each other. There's some details I'm skipping, but let's say it this way. And then in this case, it's hard, and I'm not going to show you how to do it, but it's the same but harder. Okay, so now why is this good for us? So I've pre-colored my R, and then I update it 3 times, and I do this for every pre-coloring, and I know that for every pre-coloring I get something I get an abstraction, right? After I've done this, I tried this coloring, I updated, and that's bad. That doesn't have a coloring. I've done another pre-coloring, I updated, and that's bad. That doesn't have a coloring. So I take the union of all of this stuff. I take R, and then the abstraction I get from this coloring, the abstraction I get from that coloring, the abstraction I get from that coloring, and that's still a subgraph of the graph I started with, and that's not colorable. So then if you think about it for a minute, that means that is exactly the graph you started with. So then what happened? So I have, right, so now let's focus on one pre-coloring of R, and I update it 3 times. Now everybody's list is size at most 2, and this contains, this contains an abstraction. This contains an abstraction, which we know is not too big, right? So here it is. This is the abstraction I get for this pre-coloring. Then I tried some other pre-coloring. I get some other abstraction. Again, I know it's not too big because that's an abstraction where everybody has lists of size 2, and I have the second step where I will prove that. And so on and so forth. So you take the union of all these pre-colorings, and they know, and you take the union of all these abstractions, you know each of them is not too big. You know there aren't too many of them because their number is just the number of 3 colorings. So where is the trick? The problem is that they don't need to completely contain R, right? It's almost true that you prove that your whole graph is just the union of not too many graphs, each of which has bounded size. But that's not exactly true, because there's this R which might be huge. And maybe your abstractions did not contain all of R. You only know what you had to contain outside of R. So then what do I know? I know that my whole graph that I started with has this huge, potentially huge R sitting in it, but otherwise it's not very big. And that's where you start using the fact that R is actually somehow a very simple graph. Because what you say is, well, this is small, right? This is at most 1 million vertices, or a lot of vertices, but bounded number. Then how many different types of vertices are there in R? Well, not that many. It's only however many different neighborhoods you can have here, which is still bounded size. So all of R is somehow partitioned into bounded many sets, each of which has a fixed neighborhood out here. And then you say, well, but R wasn't so complicated to begin with, right? So this is somehow partitioned into a bunch of sets, and this is partitioned into a bunch of sets by their neighborhoods outside. Well, but this is supposed to be a minimal abstraction. Why am I keeping more than one vertex from this set? They all have the same neighbors outside. They all have the same neighbors inside. So actually, I don't need to do that. It's just enough to keep one vertex from here, right? If it was a minimal abstraction, there would just be one vertex here. And so, right? And so then you prove that your whole graph is small. So again, the idea is, at the moment, your R is very big, but there are only boundedly many types of vertices as far as neighbors outside are concerned, and there are only boundedly many types of vertices as far as neighbors inside are concerned, and then you actually, in the minimal abstraction, it wouldn't be as big as you thought. It would only be bounded size. So that's how you do this. And then just a very brief explanation of the second half. So the second half says, if I have a graph and it's free of whatever it is that I care about, and at the level of detail I'm going to do it in, it completely doesn't matter what it's free of, and all these have size 2, right? So abstraction, all these have size 2, free of whatever, then it has bounded size. So then what you do is the following. So you start with a vertex, and let's say it has list 1, 2. And let's try and color it 1. So there is some other vertex whose color it fixes, it forces. Let's say it had a neighbor with color 1, 3, so then this has to be colored 3. And I'm going to write 1 sub 2, meaning I colored him 1, and I had 2 left. And then this, I colored him 3, and let's say it has 2 left. And then I can go further, and let's say this is, I don't know what, 2, 3, so now I'm going to color this 3, it has 2 left. This had 1 left, I guess, and so on and so forth. So you have this forcing pass. And if you can just get through the whole graph with this forcing pass or some union of, or some vertices are not in the forcing pass, you can start over, then the graph is colorable. But the graph is not colorable. And what that means is that you keep going along a forcing path like that, and eventually you get a contradiction. Eventually you get somebody who was forced to be colored X, but there's somebody else who was already colored X. So that's when I decided to color him 1. Now let's try to color him 2. And again, it's going to be the same kind of deal. And that's it. This graph is not colorable. I tried to color him 1, and I got a contradiction. I tried to color him 2, and I got a contradiction. So that's the whole abstraction. This union of 2 paths where I got contradictions, that's my whole abstraction. So if I could prove that a forcing path like this, or what we call a propagation path, must have bounded lengths, then I'm done. And you basically can't, because so you look at this path, and suppose it's very long, then, so my graph doesn't have, let's say I'm doing the case of no P6. So my graph doesn't have a P6, my graph doesn't have a very large clique, because, that's how I started. But it does have a very long path. That means it has a huge complete bipartite subgraph. Right? Just this path has a huge complete bipartite subgraph. So that means in this path, there's a ton of chords. There's a ton of edges that go between vertices that are not consecutive in the path. On the other hand, you'd think if you have an edge like that, well, maybe you could shortcut. And it's true. Usually you can shortcut. The only time you cannot shortcut is the edge goes between somebody of shape 3, 1, somebody I colored 3 and had 1 left, and somebody of shape 1, 2, meaning I colored him 1 and had 2 left. Again, so it doesn't matter exactly the details, but what matters is that this tells me there are a lot of chords. This tells me chords are fairly rare and there's a lot I know about them. And then you keep thinking about it and it turns out not both the statements are true. And that's how you finish the proof. Thank you very much.
Are there any questions for Maria?
It was crystal clear. Excellent.
Earlier on, you mentioned that there are problems that are agency but not NP complete, and neither do we know polynomial time algorithm.
I don't think I mentioned that. It's true, but I don't think I don't think I mentioned that. I think what I was talking about is that there are problems where there are unbounded many abstractions, but you can still test if there's a coloring.
Have you tried, for instance, the 3 problems which are not NP complete, have you tried showing that they're complete for other classes in between NP and P?
I don't know what I said, but that's not what I meant to say.
Are there any more questions?
Yeah, so earlier you described in your algorithm that you're guessing 20 verses. I didn't catch whether they were sitting inside some bounded part of the graph, or does that say something about running time?
That says something about the running time, yeah. That's where you pay in running time. When you guess 20 vertices, you branch into, yeah. Oh, some value of 20. Yeah.
Are there any further questions?
Do you have any conjecture for 3 provided graphs? What can the polytime algorithm do there?
Yeah, no, I wish I had. Every time I start thinking about it, whatever direction I'm thinking, I conjecture the other direction. But I don't know. I really don't know.